the recording and Dima, let us take a few minutes for the questions. Yes.
Yes, of course.
Okay, let us start.
Thank you very much. It's a pleasure to take part of the community of integrable systems, and it's my particular pleasure to talk about full Toda system, which is interesting from very different point of views. It shares some structure properties of integrable systems. It is responsible for some efficient calculating methods like QR decomposition, and it has some very important geometric properties, and I will talk about these aspects today. So my here are just some keywords related to this talk. So the full Toda system is related to the geometry of Lake varieties, and the QR algorithm is also in the core of its mathematical nature. And my talk is based on some joint works with Yuri Chernyakov, Georgy Sharygin, and Alexander Sorin. Here is the plan, and I will start by some definitions. So the classical open Toda chain is defined as a Hamiltonian system with a Hamiltonian presented here. So it has a kinetic term and the potential exponential term. And the canonical Poisson bracket in terms of variables P and Q, which is given here. And this, the dynamic, the Hamiltonian dynamics has the Lax representation in this form with the Lax operator, which is a symmetric three-diagonal matrix. The matrix coefficients which are called the Flaschke coordinates in the theory of open Toda chain. They are given by these formulas. And the Hamiltonian, which defines the principal flow, the principal Hamiltonian flow, is a spectral invariant for the Lax matrix, which is given by the trace of the square of the Lax matrix. The QR algorithm, it is the following procedure. So let A be a real matrix. We define a series of matrices AK such that the step from AK to AK plus 1 is given by the following procedure. Consider the QR decomposition of the matrix AK. So Q is orthogonal, R is upper triangular. And just by twisting the components, we create a new matrix AK plus 1, which is RKQK. It appears that this discrete dynamical system, so it is efficient way to calculate eigenvalues and eigenvectors of a matrix A. More precisely, the matrices AK are similar for different K, so they share the same eigenvalues, and for example, for a symmetric matrix A, this series AK tends to the diagonal matrix, which is a diagonal matrix with the same eigenvalues. And it appears that this method is quite efficient, so it's very quick as a calculating methods of eigenvalues and eigenvectors for a symmetric matrix A. So there is a classical theorem about the open Toda chain, which make a relation between the dynamic of this system with the QR algorithm. So let L0 be a symmetric three-diagonal matrix, and consider the QR decomposition of the exponential of this matrix with some matrices Q and R, which Q is orthogonal, R is upper triangular, which now depends on the time t, and compose the matrix L of t, just conjugating by the orthogonal matrix Q. It appears that this matrix L of t is a solution for the Toda system with the initial value given by L0 here. So it means that the dynamics of the system can be solved by just by calculating the QR decomposition of some trivial dynamics. Moreover, if L of t is the solution of the Toda system, then the matrices mk, which is the exponential of L of k in discrete series of values of the parameter k, are matrices obtained by the QR algorithm. So the exponentials of the lax operating in the discrete moments of time are just the steps of the QR decomposition method. So, another way to calculate the eigenvalues, it is to turn on the Toda system dynamics and to consider the t to infinity limit and to obtain the eigenvalues if you have the quite quick way to calculate the Toda system dynamics. There is a very natural generalization of the open Toda chain, which is called the full Toda chain, and I use here the full symmetric version of the full Toda chain. There is another very important case. It is the constant full Toda system, and it is a subject of one of the next talks on your seminar. So let us consider a generic symmetric real matrix A with values small a ij, and eij are the matrix units. The elements a small aij I will associate with the generators of the Lie algebra B minus, the Lie algebra of Borel lower triangular matrices. We also define the partial matrices AK of lambda, which are obtained by just subtracting k right columns of the matrix A. Of the matrix A minus lambda identity matrix and k upper rows of this matrix. So we just subtract some right part and some upper part. And the result of Date and his co-authors states the following, that the complete set of roots of all characteristic polynomials of such matrices constitutes a commutative family with respect to a Poisson bracket induced by the Kirillov Poisson bracket on this Poisson algebra, symmetric algebra of the lower triangular Borel subalgebra. Another way to introduce such this commutative family is to consider affine coordinates on this set of projective coordinates. So if we divide all the polynomials in this family by the highest terms, we obtain polynomials, unimodular polynomials. Those coefficients are commutative, Poisson commutative rational functions on B minus. Okay, there is a way to incorporate all these integrals into a single generating function. To do it, we introduce an anti-diagonal matrix omega epsilon of this form. So on the anti-diagonal, we have powers of parameter epsilon in this way. And we consider a characteristic polynomial of such matrix. So it is a rational metric, a rational function on Z. The residue of this function is a matrix A, which is generating matrix of functions on our Poisson manifold. There is a magnetic term of such special kind in terms of, for example, of the Lax operator for the Gaden model. And we consider its characteristic polynomial. It is a polynomial on variables z-1, lambda, and epsilon. Then we consider its decomposition into the sum of homogeneous components on z-1 and lambda. Each such component, I, k, z, lambda, epsilon, is a polynomial on epsilon, with the leading term, the smallest term, like this. So it appears that our the generators of the Deift commutative family are just the coefficients of these leading terms in decomposition on epsilon of such homogeneous component of this generating series, and it is an important tool to perform the quantization for the system. I will talk a little bit later about it. The QR decomposition is principally related to the Adler-Kostant-Symes scheme known in the theory of integrable systems. I will recall the essence of this method. Let Lie algebra G admit decomposition into the sum of two its subalgebras, G plus and G minus. Here we interpret the symmetric algebra of the linear space G as an algebra of function on the dual space of G star. And there is a natural projection map I from SG to SG plus, which is related with the natural decomposition of the symmetric algebra, the algebra of polynomials, in such a sum. So the lemma, the AKS, one of the variants of AKS lemma is the following one. Let F and H be two G plus invariant elements of this symmetric algebra and commute with respect to the Kirillov constant bracket on this algebra. Then their images IF and IH commute with respect to the Kirillov-Poisson bracket on this subalgebra, on this symmetric algebra. So the principal observation is the following: that the full Toda system, the full symmetric Toda system, is related, can be obtained by the scheme applying to this type of decomposition. So SLN can be decomposed as the direct sum of B minus and the compactly subalgebra, and the space of functions on symmetric matrices is just the symmetric algebra of B minus. So the map I is a projection along the compact Lie subalgebra. So this approach, so the approach of generating series of all these Hamiltonians allows to perform the quantization, and I will I will say some words about it. So let us consider a matrix B. Those elements are not numbers, but elements of some associative algebra. And we use the following definition of the non-commutative determinant. Like this, so it is a completely symmetrized determinant of a matrix with non-commutative elements. So we consider just all the products in all possible orders of the matrix element of matrix B. Let us consider now the generating series of the similar form to the classical one. So there is a part related with the Lax operator. There is a matrix representing a magnetic term of the model, and in place of the spectral parameter lambda, I take the partial derivative over the parameter z. And the matrix A now it is a matrix with elements in not in the Lie algebra but in its universal enveloping algebra. So I consider its elements as generators of the associative algebra, which is a universal enveloping algebra of the corresponding Lie algebra. And apply this non-commutative determinant to this form, and also decompose this expression into the sum of homogeneous parts on Z and D over Z. And the leading terms of these expressions generate, so they produce some coefficients. So the differential operator on Z, and the coefficients are just some elements of our non-commutative algebra, of the universal enveloping algebra. We could consider decomposition of the universal enveloping algebra into the sum of some subspaces. We have just to choose some normal ordering to do it, and we consider A plus as a projection of an element A in U in the universal enveloping algebra to the first summand. We also need to consider localization of this associative algebra with respect to the multiplicative set as generated by the principal terms in the polynomials generating the Hamiltonians of the full Toda system. Okay, so the theorem states the following, that these quotients here is the coefficients of the characteristic polynomial. It's positive part, so the projection to this summand divided by the highest term of the Hamiltonian of the characteristic polynomial, generate a commutative subalgebra in a localization of the universal enveloping algebra with respect to this multiplicative set, which is a quantization of the classical full Toda symmetric subalgebra. Okay. Now I will talk about some geometric application of this interesting system. So it was applied to the geometry of intersection of real Brouwer cells. And I need to introduce some notation. So let G be real Lie algebra. Those complexification is GC. and moreover, I suppose that G is a normal or non-split real form. Just as a remark, I recall the definition. Let theta be a Cartan involution, so it is such an automorphism of the Lie algebra G, which is an involution and which is related with the Killing form in this way. So this form Bxt y is positive definite. Then we can define the eigen subspaces of this involution. The subspace k correspond to the eigenvalue -1 of the Cartan involution. The subspace p correspond to the eigenvalue 1. And these subspaces represent the two-graded Lie algebra structure. So K is a subalgebra, P is a module over K, and there is this relation for the commutators of elements in this part. So A is a maximal commutative Lie subalgebra in a subspace P. Then the real form is called normal or non-split if A coincides with the maximal commutative subalgebra in a whole Lie algebra G. Okay. Okay, I need some more definitions. The Weil group of G can be defined as a quotient group of the normalizer over the centralizer of the maximal torus H. Okay. The Breuer order in a Coxeter group, for example, in the Weil group, with a generating set like this, is a unique partial order in this group determined by the following rule. We say that W precedes W prime. It's a minimal word of W prime in the chosen alphabet. Representing W prime has the form like this. So the end of this word is just the word, a minimal word of an element W. Length of this word are called lengths of elements and are denoted by these letters A. Okay, we can now define the Breuer cells and dual Breuer cells to each related to each element of the Weil group of the Lie algebra G. So they are orbits of elements of Weil group in the Fleck variety with respect to the action B plus and B minus on this space. So the theorem which we managed to prove with my colleagues state the following: that the intersection of a Breuer cell corresponding to an element W and the dual Breuer cell corresponding to an element W prime in the real case is non-empty if and only if W prime precedes W in Breuer order, and moreover, in this case, if this intersection is non-empty, the dimension of the intersection is just the difference of lengths of these elements. The statement was known before in the complex situation, but the real version was demonstrated using the existence, the properties of the full Toda system. I will give some details how these are related. So let us consider the Toda flow corresponding to some root system phi. So here is an expression of the Lax operator for the M operator, which plays a role in the Lax form of this dynamics, and these dynamics can be rephrased on the level of the corresponding compact group. So let us define a dynamic on elements phi from the corresponding compact group. We consider the flow which is given by this expression. Here M is given by this antisymmetric matrix. Here psi act on a diagonal matrix lambda. We apply M at this point to psi. So in fact, this flow is related to the standard flow of the Toda system by this rule. So if we can solve this equation for psi, we can solve the equation for then L of t is a solution for the Toda flow on the space of on Lax operators from the space of symmetric matrices in the case of root system A n-1. So this construction can be applied to the following observation, that Brouwer cells and dual Brouwer cells, the intersection are invariant surfaces of these vector fields. And principally due to this observation, we calculated the dimension of the intersection of Brouwer cells. Okay. And the next part of my talk, the final part of my talk, is a generalization of the QR method for the full symmetric Toda system. Let us introduce some notations. Ck of L is just the left lower minor of the matrix L. And now we introduce some matrix valued function. Some matrix valued functions on the space of Lax operator. They are given by this this expression. First remark that the first matrix valued operation from this list is just the Lax operator, and here an example for the second term in this series of matrix operations. So to 2 of L applied to a vector V is given by this expression. A theorem due to our recent work with Chernyakov and G. Sharygin. Let us consider the vector field Tk on the space of symmetric matrices, which is given by this formula. Here, in place of an operator L, we consider this tensor operation tau k of L. The solution of the system of this equation can be obtained by the following procedure. Let L0 is initial point in the space of symmetric matrices. Let us consider the QR decomposition of the exponential, but else in this exponential we get this nonlinear matrix operation applied to the initial point, initial value of the Lax operator. So we make it QR decomposition, but here in the inverse order. Then this operator is a solution for this system, for this vector, for this equation with the initial value L0. And it can be demonstrated that this flow is a Hamiltonian vector flow with respect to the Poisson structure so it is the symplectic structure. I'm sorry, this Poisson structure introduced by the Kirillov constant bracket on B minus, which is the initial Poisson structure of the Toda system, and the Hamiltonian function, this one, which is one of the Hamiltonians of date family. And this observation can be extended to all flows of the full symmetric Toda system. To do this, we introduce some new notation. So here X, I, J are elements of the Lax operator L. Okay, and we apply a differential operator of this type to such a determinant and decompose it into powers of lambda and consider the elements of this form, which are now linear operators. So we showed that the QR decomposition method gives solution of the higher Dave flows of all Dave flows, and to do it, we have to make a QR decomposition of the exponential where we applied this linear operator to the element, to the initial value of the Lax operator. And then this operator L of t, which is a conjugation of L0 by Q, solves the equation, solves the Hamiltonian equation of the corresponding high date flow. So this is the result. And I'd like to propose some open questions. So the symmetric full Toda system is super integrable. It means that there is a bigger family of integrals of a part of isospectral Hamiltonian flows. The date family is a part of them. There are many others which are related with towers of parabolic subgroups. So the first question is to find solutions for alternative families of integrals in this case. Another question we are working on this question now with my colleagues. But principally, it's a geometry of intersection of orbits of orthogonal subgroups from this tower of orthogonal subgroups and the level sets of the complete family of integrals. And maybe the last question for today. is a quantum interpretation of the QR method of solution of the system. It is interesting even in the open Toda chain case. Thank you very much.
Thank you. Very quickly, very quickly, but very nice. So I have the following question. It is known that usual three diagonal Toda lattice is a B Hamiltonian system. What about the full Toda lattice?
I suppose that it is not the case in the full Toda case.
Oh, because Hamiltonian systems are very close to super integrable systems. In the both cases, we can express the angle where variables in term of the good well defined functions on the whole phase space. So if we have super integrability, we have a B Hamiltonian vector field, in fact. So maybe there are some relations in the case of the full Toda lattice too.
Sorry.
I suppose that if the second Poisson structure exists, it's of very different analytic nature, so it's not polynomial.
I'm sorry if I'm allowed to just mention. I'm sorry if I'm allowed to mention that bi-Hamiltonian structures are known for the full constant Toda system. As far as a full symmetric, I have never heard about this.
Yes, I have this similar intuitive opinion.
Maybe, I don't know. Any other questions?
Yeah, can I ask a few questions? Like, can you turn to the second to last page where you list the several questions?
Sorry, I don't.
So can you turn up like a little bit, like one page? Yeah, just a one page, like
Here.
No, like okay, the last page maybe. Yeah, so the next one. Okay, so I have two questions. Like the first one is for example, for four constant Toda lattice, for symmetric Toda lattice, you said like it's we know that it's a super integrable.
Yeah.
Because you can have different parabolic subgroups, like towers of parabolic subgroups. So, but can we obtain like all of them like at once?
Could you repeat it?
So we know that like for symmetric Toda lattice is super integrable.
Just the last sentence.
Okay, so yeah, could we obtain like other different ones, like just in one shot? Like because you take one chain of parabolic subgroups, and you get one commutative family.
Yeah.
And then but there are maybe like other towers of parabolic subgroups, and you get another family. So for example, if I consider just for example SL4, then I know that it has like two different.
Yes, it's for sure.
Yeah. Right. But is there a universal way that I can get other functions that can be act as Hamiltonian, higher Hamiltonians?
I don't know the universal way. It is occasionally the case. So ordinarily, it is like this. But there is a very important property of the commutativity. So the invariance with respect to the tower of parabolic subgroups, it is a simple part of this story, but we also need to construct the we start in the framework of Adler-Kostant-Symes scheme. We have to start with the commutative family.
Okay.
But it possibly it should be true. It should be true.
Okay. So another question is like I'm quite interested in the part with flag variety. So you said you use the Toda system to prove a theorem like in the real slice on the real slice of the dimension of flag variety. Yeah, that was quite interesting. And so yeah, so can you just say briefly like how this theorem is proved?
But you see, we can parameterize the integral lines of this flow. So we can calculate the dimension of the tangent space. So from the point of view of Toda system, it's a simple part.
Sorry, if I'm allowed, may I make a remark? I mean, the key step towards this proof is that Toda system on flag variety, actually gradient flow. And therefore, you know how it should go from one point to another. And you just count the dimensions of stable and unstable manifolds at each point. And then there is virtually no other way they can go, these flows can go.
Yeah, so you just said it's a gradient flow of what? Of
vector fields on some function on SON.
Okay, so let me make a guess, like can trace of L square, for example, can this function
almost. It's not quite trace of L square, it's trace of L times certain commutator.
Okay.
And which is even more interesting in it to modify the the Killing form to obtain the gradient. It's not just the Killing form that you use.
Okay, I see. Okay, yeah, that's quite interesting. So you can, so you can use this kind of thing. For example, can you use this kind of thing to? I mean, what you just described is basically like a Morse spot. So can you use this thing to calculate the real cohomology of a flag variety?
Never actually tried to do this, to be sure, but I think yes, actually, it is Morse bot. That's true. It's even Morse, I think, in the case of the split. Well, when I give English a different, then they can use it is just Morse. But in general case, it is Morse bot, and but I had never tried to do this. Never looked into this because, well, I thought it was more or less known flag varieties, except for some exotic cases.
I mean, for complex flag varieties, yeah, but for real ones, I think it's only known like very recently.
I see. Then yeah, that's a good question. Then it's true. Need to check this.
Okay. Thank you.
Yeah.
Thank you. Very interesting question. Andrei?
Well, any more questions? I believe not. Then thank you for your talk.
Thank you very much for invitation.
Well, I will stop.